Hello and welcome to a new series of videos. In this series we are going to read the book called Crafting Interpreters, written by Robert Nystrom. I'm sorry if I don't pronounce his name correctly, but I'm not American. And in this book walks the reader through a process of writing an interpreter. The first part of the book builds an AST interpreter, like a tree walking interpreter, which is a very high level concept and relatively slow. And in this book, the AST, the tree walking interpreter, is written in Java, and the second part of the book is a bytecode virtual machine, and that virtual machine part is written in C. And if you have watched any of my previous Kernighan and Ritchie videos, you may have seen me quoting parts of this book because it's a very good book. And I actually did go through the first part, the tree walking interpreter part, about 2 years ago, and I wrote the tree walking interpreter in Rust. And this time we are going to write it in Go, because that was the result of a half a day long poll on my YouTube wall. So if you're hoping to see some Rust or Zig or Swift or whatever, you probably should go and watch another video. But anyway, I'm going to quickly walk through chapters 1 and 2 of this book because nobody really likes reading introductions, and I am pretty sure everybody wants to see at least some code being written in this video. And if you don't have this book yet, you can just read it for free with no strings attached on craftinginterpreters.com. And maybe before we start, I'm going to show you some of the things you can do with when you finish this book. The language you are going to implement is called logs, and it's kind of it looks like a C family language, kind of like JavaScript. It has closures, it is interpreted, and it's very simple. It basically only has the whole standard library for logs only consists of a print function, basically. And I'm going to demo the interpreter I wrote 2 years ago. This is the source code for the main function written in Rust. And I'm going to show you that it can indeed run the script that I downloaded from this website. So when we run this script, it also presents a Fibonacci sequence. And I know this may look kind of underwhelming, but believe me, it's actually a lot of fun, and you can learn a lot about programming languages in the process. Also, I do realize that some people may hate me for doing this in a light mode, so I'm going to turn on Dark Reader. Great. So without further ado, let's open the web format, and I'm probably going to skim over chapter 1. Okay. Introduction. Fairy tales are more than true, not because they tell us that dragons exist, but because they tell us that dragons can be beaten. J.K. Chesterton by way of Neil Gaiman, Coraline. Okay. Yeah, so this is a lot of text. None of this is directly related to programming. Maybe I'll jump here. Why learn this stuff? Every introduction to every compiler book seems to have this section. I don't know what it is about programming languages that causes such existential doubt. I don't think ornithology books worry about justifying their existence. They assume the reader loves birds and start teaching. But programming languages are a little different. I suppose it is true that the odds of any of us creating a broadly successful general-purpose programming language are slim. The designers of the world's widely used languages could fit into a Volkswagen bus, even without putting the pop-top camper up. If joining that elite group was the only reason to learn languages, it would be hard to justify. Fortunately, it isn't. Little languages are everywhere. For every successful general-purpose language, there are 1,000 successful niche ones. We used to call them little languages, but inflation in the jargon economy led to the name domain-specific languages. These are pigeons tailor-built to a specific task. Think application scripting languages, template engines, markup formats, and configuration files. Almost every large software project needs a handful of these. When you can, it's good to reuse an existing one instead of rolling your own. Once you factor in documentation, debuggers, editor support, syntax highlighting, and all the other trappings, doing it yourself becomes a tall order. But there is still a good chance you'll find yourself needing to whip up a parser or other tool when there isn't an existing library that fits your needs. Even when you are reusing some existing implementation, you'll inevitably end up needing to debug and maintain it and poke around in its guts. Languages are great exercise. Long-distance runners sometimes train with weights strapped to their ankles or at high altitudes where the atmosphere is thin. When they later unburden themselves, the new relative ease of light limbs and oxygen-rich air enables them to run farther and faster. Implementing a language is a real test of programming skill. The code is complex and performance critical. You must master recursion, dynamic arrays, trees, graphs, and hash tables. You probably use hash tables at least in your day-to-day programming, but do you really understand them? Well, after we've crafted our own from scratch, I guarantee you will. While I intend to show you that an interpreter isn't as daunting as you might believe, implementing one well is still a challenge. Rise to it and you'll come away a stronger programmer and smarter about how you use data structures and algorithms in your daily job. One more reason. The last reason is hard for me to admit because it's so close to my heart. Ever since I learned to program as a kid, I felt there was something magical about languages. When I first tapped out basic programs one key at a time, I couldn't conceive how basic itself was made. Later, the mixture of awe and terror on my college friends' faces when talking about their compiler's class was enough to convince me language hackers were a different breed of human, some sort of wizards granted privileged access to arcane arts. It's a charming image, but it has a darker side. I didn't feel like a wizard, so I was left thinking I lacked some inborn quality necessary to join the cabal. Though I've been fascinated by languages ever since I had doodled made-up keywords in my school notebook, it took me decades to muster the courage to try to really learn them. That magical quality, that sense of exclusivity excluded me. Side note, and its practitioners don't hesitate to play up this image. Two of the seminal texts on programming languages feature a dragon and a wizard on their covers. And these seminal works would be this one, Compilers, Principles, Techniques, and Tools. And the second one is a 404. When I did finally start cobbling together my own little interpreters, I quickly learned that, of course, there is no magic at all. It's just code, and the people who hack on languages are just people. There are a few techniques you don't often encounter outside of languages, and some parts are a little difficult, but not more difficult than other obstacles you've overcome. My hope is that if you've ever If you felt intimidated by languages and this book helps you overcome that fear, maybe I'll leave you just a tiny bit braver than you were before. And who knows, maybe you will make the next great language. Someone has to. How the book is organized. This book is broken into 3 parts. You're reading the first one now. It's a couple of chapters to get you oriented, teach you some of the lingo that language hackers use, and introduce you to locks, the language we will be implementing. Each of the other 2 parts builds one complete locks interpreter. Within those parts, each chapter is structured the same way. The chapter takes a single language feature, teaches you the concepts behind it, and walks you through an implementation. It took a good bit of trial and error on my part, but I managed to carve up the 2 interpreters into chapter-sized chunks that build on the previous chapters but require nothing from later ones. From the very first chapter, you'll have a working program you can run and play with. With each passing chapter, it grows increasingly full-featured until you eventually have a complete language. Aside from copious, scintillating English prose, chapters have a few other delightful facets. Okay, I can't hear it. Facet. Facet. Facets. 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 Chapters have a few other delightful facets. The code. We are about crafting interpreters, so this book contains real code. Every single line of code needed is included, and each snippet tells you where to insert it in your ever-growing implementation. Many other language books and language implementations use tools like Lex and Yak, so-called compilers, that automatically generate some of the source files for an implementation from some higher-level description. There are pros and cons to tools like those, and strong opinions. Some might say religious convictions on both sides. Side note. Yak is a tool that takes in a grammar file and produces a source file for a compiler, so it's sort of like a compiler that outputs a compiler, which is where we get the term compiler. Yak wasn't the first of its ilk, which is why it's named Yak, yet another compiler. A later similar tool is Bison. Bison, how do you pronounce Bison? Bison? Bison. A later similar tool is Bison, named as a pun on the pronunciation of yak like yak, which is, if you find all these little self-references and puns charming and fun, you'll fit right in here. If not, well, maybe the language nerd sense of humor is an acquired taste. Okay, back to the main text. We will abstain from using them here. I want to ensure there are no dark corners where magic and confusion can hide, so we'll write everything by hand. As you'll see, it's not as bad as it sounds, and it means you will really understand each line of code and how both interpreters work. A book has different constraints from the real world, and so the coding style here might not always reflect the best way to write maintainable production software. If I seem a little cavalier about, say, omitting private or declaring a global variable, understand I do so to keep the code easier on your eyes. The pages here aren't as wide as your IDE, and every character counts. Also, the code doesn't have many comments, that's because each handful of lines is surrounded by several paragraphs of honest-to-God prose explaining it. When you write a book to accompany your program, you are welcome to omit comments too. Otherwise, you should probably use / a little more than I do. While the book contains every line of code and teaches what each means, It does not describe the machinery needed to compile and run the interpreter. I assume you can slap together a makefile or a project in your IDE of choice in order to get the code to run. Those kinds of instructions get out of date quickly, and I want this book to age like XO brandy, not backyard hooch. What's hooch? Okay, strong alcohol, especially whiskey. Snippets. Since the book contains literally every line of code needed for the implementations, the snippets are quite precise, also because I try to keep the program in a runnable state, even when major features are missing. Sometimes we add temporary code that gets replaced in later snippets. A snippet with all the bells and whistles looks like this. In the center you have the new code to add. It may have a few faded outlines above or below to show where it goes in the existing block. Okay, yeah, I'm going to skip this part. Asides. Challenges. Each chapter ends with a few exercises. Unlike textbook problem sets, which tend to review material you already covered, these are to help you learn more than what's in the chapter. They force you to step off the guided path and explore on your own. They will make you research other languages, figure out how to implement features, or otherwise get you out of your comfort zone. Vanquish the challenges and you'll come away with a broader understanding and possibly a few bumps and scrapes. Or skip them if you want to stay inside the comfy confines of the tour bus. It's your book. A word of warning, the challenges often ask you to make changes to the interpreter you are building. You'll want to implement those in a copy of your code. The later chapters assume your interpreter is in a pristine, unchallenged state. Design note. Most programming language books are strictly programming language implementation books. They rarely discuss how one might happen to design the language being implemented. Implementation is fun because it is so precisely defined. We programmers seem to have an affinity for things that are black and white, ones and zeros. Personally, I think the world needs only so many implementations of Fortran 77. At some point, you find yourself designing a new language. Once you start playing that game, then the software-human side of the equation becomes paramount. Things like which features are easy to learn, how to balance innovation and familiarity, what syntax is more readable and to whom. Okay. We'll write our first interpreter JLogs in Java. Actually, we will write it in Go, but the source code of the book is going to be written in Java, and I'm going to attempt to translate it into Go on stream, on the video. I'm not even going to try to run the Java code. I didn't do it the last time, and I don't intend to do it this time. I don't write any Java. The focus is on concepts. We will write the simplest, cleanest code we can to correctly implement the semantics of the language. This will get us comfortable with the basic techniques and also hone our understanding of exactly how the language is supposed to behave. Yeah, the second interpreter. So in the next part, we start all over again, but this time in C. C is the perfect language for understanding how an implementation really works, all the way down to the bytes in memory and the code flowing through the CPU. A big reason that we are using C is so I can show you things C is particularly good at, but that does mean you'll need to be pretty comfortable with it. You don't have to be the reincarnation of Dennis Ritchie, but you shouldn't be spooked by pointers either. Okay, great. Design notes. Okay, next chapter. Chapter 2, a map of the territory. You must have a map, no matter how rough. Otherwise, you wander all over the place. In The Lord of the Rings, I never made anyone go farther than he could on a given day. We don't want to wander all over the place, so before we set off, let's scan the territory charted by previous language implementers. It will help us understand where we are going and the alternate routes others have taken. First, let me establish a shorthand. Much of this book is about a language's implementation, which is distinct from the language itself, in some sort of Platonic ideal form. Things like stack, bytecode, and recursive descent are nuts and bolts one particular implementation might use. From the user's perspective, as long as the resulting contraption faithfully follows the language's specification, it's all implementation detail. We're going to spend a lot of time on those details, so if I have to write language implementation every single time I mention them, I'll wear my fingers off. Instead, I'll use language to refer to either a language or an implementation of it, or both, unless the distinction matters. The parts of the language. Engineers have been building programming languages since the dark ages of computing. As soon as we could talk to computers, we discovered doing so was too hard, and we enlisted their help. I find it fascinating that even though today's machines are literally a million times faster and have orders of magnitude more storage, the way we build programming languages is virtually unchanged. While the area explored by language designers is vast, the trails they've carved through it are few. Not every language takes the exact same path. Some take a shortcut or two, but otherwise they are reassuringly similar, from real Admiral Grace Hopper's first COBOL compiler all the way to some hot new transpiled to JavaScript language whose documentation consists entirely of a single poorly edited README in a Git repository somewhere. Side note: there are certainly dead ends, sad little cul-de-sacs of CS papers with zero citations and now forgotten optimizations, but only made sense when memory was measured in individual bytes. Back to the main text. Eventually we reach the peak. Okay, so this is the map of the path this book is going to take. And okay, maybe I'll read the explanation. I visualize the network of paths an implementation may choose as climbing a mountain. You start off at the bottom with the program as raw source text, literally just a string of characters. Each phase analyzes the program and transforms it to some higher level representation where the semantics, what the author wants the computer to do, become more apparent. Eventually, we reach the peak. We have a bird's eye view of the user's program and can see what their code means. We begin our descent down the other side of the mountain. We transform this highest level representation down to successively lower level forms to get closer and closer to something we know how to make the CPU actually execute. Let's trace through each of those trails and points of interest. Our journey begins on the left with the vertex of the user's source code. Var average equals min plus max divided by 2. The first step is scanning, also known as lexing, or if you are trying to impress someone, lexical analysis. They all mean pretty much the same thing. I like lexing because it sounds like something an evil supervillain would do, but I'll use scanning because it seems to be marginally more commonplace. A scanner or lexer takes in the linear stream of characters and chunks them together into a series of something more akin to words. In programming languages, each of these words is called a token. Some tokens are single characters like left bracket and comma. Others may be several characters long, like numbers 1 to 3, string literals, and identifiers. Lexical comes from the Greek root lex, meaning word. Some characters in a source file don't actually mean anything. White space is often insignificant, and comments by definition are ignored by the language. The scanner usually discards these, leaving a clean sequence of meaningful tokens. Where was I? Some characters in a source file don't actually mean anything. White space is often insignificant, and comments by definition are ignored by the language. The scanner usually discards these, leaving a clean sequence of meaningful tokens. var average equals left bracket min plus max right bracket /2 semicolon. The next step is parsing. This is where our syntax gets a grammar, the ability to compose larger expressions and statements out of smaller parts. Did you ever diagram sentences in English class? If so, you've done what a parser does, except that English has thousands and thousands of keywords and an overflowing cornucopia of ambiguity. Programming languages are much simpler. A parser takes the flat sequence of tokens and builds a tree structure that mirrors the nested nature of the grammar. These trees have a couple of different names: parse tree or abstract syntax tree, depending on how close to the bare syntactic structure of the source language they are. In practice language, hackers usually call them syntax trees, ASTs, or often just trees. So in this case, the var is equal to the result of a division by 2 of the sum of min and max. Parsing has a long, rich history in computer science. Blah, blah, blah. Static analysis. The first two stages are pretty similar across all implementations. Now the individual characteristics of each language start coming into play. At this point, we know the syntactic structure of the code, things like which expressions are nested in which, but we don't know much more than that. In an expression like a plus b, we know we are adding a and b, but we don't know what those names refer to. Are they local variables, global? Where are they defined? The first bit of analysis that most languages do is called binding or resolution. For each identifier, we find out where that name is defined and wire the two together. This is where scope comes into play. The region of source code where a certain name can be used refers to a certain declaration. If a language is statically typed, this is when we type check. Once we know where A and B are declared, we can also figure out their types. Then, if those types don't support being added to each other, we report a type error. Side note: the language we'll build in this book is dynamically typed, so it will do its type checking later at runtime. Take a deep breath. We have attained the summit of the mountain and a sweeping view of the user's program. All this semantic insight that is visible to us from analysis needs to be stored somewhere. There are a few places we can squirrel it away. Often it gets stored right back as attributes on the syntax tree itself, extra fields in the nodes that aren't initialized during parsing, but get filled in later. Other times we may store data in a lookup table off to the side. Typically, the keys to this table are identifiers, names of variables, and declarations. In that case, we call it a symbol table, and the values it associates with each key tell us what that identifier refers to. The most powerful bookkeeping tool is to transform the tree into an entirely new data structure that more directly expresses the semantics of the code. That's the next section. Everything up to this point is considered the front end of the implementation. You might guess everything after this is the backend, but no. Back in the days of yore, when frontend and backend were coined, compilers were much simpler. Later, researchers invented new phases to stuck between the two halves. Rather than discard the old terms, William Wolf and company lumped those new phases into the charming but spatially paradoxical name middle end. Okay, intermediate representations. You can think of the compiler as a pipeline where each stage's job is to organize the data representing the user's code in a way that makes the next stage simpler to implement. The front end of the pipeline is specific to the source language the program is written in. The backend is concerned with the final architecture where the program will run. In the middle, the code may be stored in some intermediate representation, IR, but isn't tightly tied to either the source or destination forms, hence intermediate. Instead, the IR acts as an interface between these two languages. Side note, there are a few well-established styles of IRs out there. Hit your search engine of choice and look for control flow graph, static single assignment, continuation passing style, and free address code. I am not going to do the research on stream. Back to the main text. This lets you support multiple source languages and target platforms with less effort. Say you want to implement Pascal, C, and Fortran compilers, and you want to target x86, ARM, and I don't know, Spark. Normally that means you're signing up to write 9 full compilers. Pascal to x86, C to ARM, and every other combination. A shared intermediate representation reduces that dramatically. You write one frontend for each source language that produces the intermediate representation, then one backend for each target architecture. Now you can mix and match those to get every combination. Side note, if you've ever wondered how GCC supports so many crazy languages and architectures like Modula 3 on Motorola 68000, what's Modula 3? Okay. Now we know. Language frontends target one of a handful of IRs, mainly Gimple and RTL. These target backends, like the one for 68K, then take those IRs and produce native code. There's another big reason we might want to transform the code into a form that makes the semantics more apparent. Optimization. Once we understand what the program means, we are free to swap it out with a different program that has the same semantics but implements them more efficiently. We can optimize it. A simple example is constant folding. If some expression always evaluates to the exact same value, we can do the evaluation at compile time and replace the code for the expression with its result. If the user typed in this, we could do all of that arithmetic in the compiler and change the code to this. Optimization is a huge part of the programming language business. Many language hackers spend their entire careers here, squeezing every drop of performance they can out of their compilers to get their benchmarks a fraction of a percent faster. It can become a sort of obsession. Yeah, I'm going to skip this. But if you are interested in optimizations, you might want to read this side note. We're mostly going to hop over that rat hole in this book. Many successful languages have surprisingly few compile time optimization. For example, Lua and CPython generate relatively unoptimized code and focus most of their performance effort on the runtime. Code generation. Okay. We have applied all of the optimizations we can think of to the user's program. The last step is converting it to a form the machine can actually run. In other words, generating code, or code gen, where code here usually refers to the kind of primitive assembly-like instruction a CPU runs and not the kind of source code a human might want to read. Finally, we are in the backend descending the other side of the mountain. From here and out, our representation of the code becomes more and more primitive, like evolution run in reverse, as we get closer to something our simple-minded machine can understand. Hang on, I want to make my cursor bigger, if I can. Okay, I don't know how to do it, but yeah, on Windows I have like a bigger cursor. We have a decision to make. Do we generate instructions for a real CPU or a virtual one? If we generate real machine code, we can get an executable that the OS can load directly onto the chip. Native code is lightning fast, but generating it is a lot of work. Today's architectures have piles of instructions, complex pipelines, and enough historical baggage to fill a 747's luggage bay. Side note. For example, the AAD ASCII adjust AX before division instruction lets you perform division, which sounds useful, except that instruction takes as operands 2 binary coded decimal digits packed into a single binary coded decimal digits packed into a single 16-bit register. When was the last time you needed BCD on a 16-bit machine? Okay, yeah, well. Speaking the chip's language also means your compiler is tied to a specific architecture. If your compiler targets x86 machine code, it's not going to run on an ARM device. All the way back into the 60s, during the Cambrian explosion of computer architectures, that lack of portability was a real obstacle. To get around that, hackers like Martin Richards and Niklaus Wirth of BCPL and Pascal fame, respectively, made their compilers produce virtual machine code. Instead of instruction for some real chip, they produced code for a hypothetical, idealized machine. Wirth called this P-code for portable, but today we generally call it bytecode because each instruction is often a single byte long. These synthetic structures are designed to map a little more closer to the language's semantics and not be so tied to the peculiarities of any one computer architecture and its accumulated historical craft. You can think of it like a dense binary encoding of a language's low-level operations. Side note, the basic principle here is that the farther down the pipeline you push the architecture-specific work, the more of the earlier phases you can share across architectures. There is a tension though. Many optimizations like register allocation and instruction selection work best when they know the strengths and capabilities of a specific chip. Figuring out which parts of your compiler can be shared and which should be target specific is an art. Okay, next section. Virtual machine. If your compiler produces bytecode, your work isn't over once that's done. Since there is no chip that speaks that bytecode, it is your job to translate. Again, you have two options. You can write a little mini compiler for each target architecture that converts the bytecode to native code for that machine. You still have to do work for each chip you support, but this last stage is pretty simple and you get to reuse the rest of the compiler pipeline across all of the machines you support. You're basically using your bytecode as an intermediate representation. Or you can write a virtual machine, a program that emulates a hypothetical chip supporting your virtual architecture at runtime. Running bytecode in a VM is slower than translating it to native code ahead of time, because every instruction must be simulated at runtime each time it executes. In return, you get simplicity and portability. Implement your VM in, say, C, and now you can run your language on any platform that has a C compiler. This is how the second interpreter we built in this book works. Runtime. We have finally hammered the user's program into a form that we can execute. The last step is running it. If we compile it to machine code, we simply tell the operating system to load the executable, and off it goes. If we compile it to bytecode, we need to start up the VM and load the program into that. In both cases, for all but the basest of low-level languages, we usually need some services that our language provides while the program is running. For example, if a language automatically manages memory, we need a garbage collector going in order to reclaim unused bits. If our language supports instance of tests, so we can see what kind of object you have, then we need some representation to keep track of the type of each object during execution. All of this stuff is going at runtime, so it's called appropriately the runtime. In a fully compiled language, the code implementing the runtime gets inserted directly into the resulting executable. In, say, Go, each compiled application has its own copy of Go's runtime directly embedded in it. If the language is run inside an interpreter or VM, then the runtime lives there. This is how most implementations of languages like Java, Python, and JavaScript work. Section 2.2, shortcuts and alternate routes. That's the long path covering every possible phase you might implement. Many languages do walk the entire route, but there are a few shortcuts and alternate paths. Single path compilers. Some simple compilers interleave parsing, analysis, and code generation so that they produce output code directly in the parser without ever allocating any syntax trees or other IRs. These single pass compilers restrict the design of the language. You have no intermediate data structures to store global information about the program, and you don't revisit any previously parsed part of the code. This means as soon as you see some expression, you need to know enough to correctly compile it. Side note, syntax-directed translation is a structured technique for building these all-at-once compilers. You associate an action with each piece of the grammar, usually one that generates output code. Then, whenever the parser matches that chunk of syntax, it executes the action, building up the target code, one rule at a time. Pascal and C were designed around this limitation. At the time, memory was so precious that a compiler might not even be able to hold an entire source file in memory, much less the whole program. This is why Pascal's grammar requires type declarations to appear first in a block. It's why in C you can't call a function above the code that defines it unless you have an explicit forward declaration that tells the compiler what it needs to know to generate code for a call to the later function. Tree-walk interpreters. Some programming languages begin executing code right after parsing it to an AST, with maybe a bit of syntax static analysis applied. To run the program, the interpreter traverses the syntax tree one branch and leaf at a time, evaluating each node as it goes. This implementation style is common for student projects and little languages, but is not widely used for general purpose languages since it tends to be slow. Some people use interpreter to mean only these kinds of implementations, but others define that word more generally, so I use the inarguably explicit tree-walk interpreter to refer to these. Our first interpreter rolls this way. Yep, this is going to say that the first interpreter we are going to write probably in the following videos is going to be a tree-walk interpreter. A notable exception is early versions of Ruby, which were tree walkers. At 1.9, the canonical implementation of Ruby switched from the original MRI, Mats's Ruby interpreter, to Koichi Sasada's YARV, yet another Ruby VM. YARV is a bytecode virtual machine. Transpilers. Okay, yeah, writing a complete backend. Yeah, so this is a longer section about transpilers. I don't think this is exactly relevant to the topic of this video, so I'm going to skip this section, and probably I'm also going to skip just-in-time compilation. I'm going to skip to section 2.3, compilers and interpreters. Now that I've stuffed your head with a dictionary's worth of programming language jargon, we can finally address a question that's plagued coders since time immemorial. What's the difference between a compiler and an interpreter? It turns out that this is like asking the difference between a fruit and a vegetable. That seems like a binary either-or choice, but actually fruit is a botanical term and vegetable is culinary, which means it is related to cooking. One does not strictly apply the negation of the other. There are fruits that aren't vegetables, like apples, and vegetables that aren't fruits, like carrots, but also edible plants that are both fruits and vegetables, like tomatoes, peas, and eggplants. Side note, peanuts, which are not even nuts, and cereals like wheat are actually fruit, but I got this drawing wrong. What can I say? I'm a software engineer, not a botanist. I should probably erase the little peanut guy, but he's so cute that I can bear to. Now, pine nuts, on the other hand, are plant-based foods that are neither fruits nor vegetables, at least as far as I can tell. So, back to languages. Compiling is an implementation technique that involves translating a source language to some other, usually lower level form. When you generate bytecode or machine code, you are compiling. When you transpile to another high-level language, you are compiling too. When we say a language implementation is a compiler, we mean it translates source code to some other form, but doesn't execute it. The user has to take the resulting output and run it themselves. Conversely, when we say an implementation is an interpreter, we mean it takes in source code and executes it immediately. It runs programs from source. Like apples and oranges, some implementations are clearly compilers and not interpreters. GCC and Clang take your C code and compile it to machine code. An end user runs that executable directly and may never even know which tool was used to compile it. So those are compilers for C. In older versions of Mats's canonical implementation of Ruby, the user ran Ruby from source. The implementation parsed it and executed it directly by traversing the syntax tree. No other translation occurred, either internally or in any user visible form. So this was definitely an interpreter for Ruby. But What of CPython? When you run your Python program using it, the code is parsed and converted to an internal bytecode format, which is then executed inside the VM. From the user's perspective, this is clearly an interpreter. They run their program from source. But if you look under CPython's scaly skin, you'll see that there is definitely some compiling going on. The answer is that it is both. CPython is an interpreter and it has a compiler. In practice, most scripting languages work this way, as you can see. The Go tool is even more of a horticultural curiosity. If you run go build, it compiles your Go source code to machine code and stops. If you type go run, it does that, then immediately executes the generated executable. So Go is a compiler. You can use it as a tool to compile code without running it. Is an interpreter. You can invoke it to immediately run a program from source, and also has a compiler. When you use it as an interpreter, it is still compiling internally. The overlapping region in the center is where our second interpreter lives too, since it internally compiles to bytecode. So while this book is nominally about interpreters, we'll cover some compilation too. Section 2.4, Our Journey. That's a lot to take in all at once. Don't worry. This isn't the chapter where you're expected to understand all of these pieces and parts. I just want you to know that they are out there and roughly how they fit together. This map should serve you well as you explore the territory beyond the guided path we take in this book. I want to leave you yearning to strike out on your own and wander all over that mountain. But for now, it's time for your own journey to begin. Tighten your bootlaces, cinch up your pack, and come along. From here on out, all you need to focus on is the path in front of you. Side note, henceforth, I promise to tone down the whole mountain metaphor thing. Okay, next chapter. Okay, so the next chapter contains a description of the logs language, which is the language we are going to implement in this series. And here we're finally going to get some code, but unfortunately I don't think we're even going to start having writing the actual implementation of the interpreter. But anyway, that's why this video is probably going to have the number 0, because it precedes the actual chapter 1 when we start writing the interpreter code. Quote, what nicer thing can you do for somebody than make them breakfast? Anthony Bourdain. Bourdain? Sorry, there are so many foreign names in this book. We'll spend the rest of this book illuminating every dark and sundry corner of the logs language, but it seems cruel to have you immediately start grinding out code for the interpreter without at least a glimpse of what we are going to end up with. At the same time, I don't want to drag you through reams of language lawyering and specificationese before you get to touch your text editor. So this will be a gentle, friendly introduction to logs. It will leave out a lot of details and edge cases. We've got plenty of time for those later. Side note, a tutorial isn't very fun if you can't try the code out yourself. Alas, you don't have a logs interpreter yet, since you haven't built one. Fear not, you can use mine, or we can use the one I wrote 2 years ago, like so. So a comment. and print hello world. Great. As that //line comment and the trailing semicolon imply, Lox's syntax is a member of the C family. There are no parentheses around the string because print is a built-in statement and not a library function. Now I won't claim that C has a great syntax. If we wanted something elegant, we'd probably mimic Pascal or Smalltalk. If we wanted to go full Scandinavian furniture minimalism, we'd do a scheme. Those all have their virtues. Side note, I'm surely biased, but I think Lox's syntax is pretty clean. C's most egregious grammar problems are around types. Dennis Ritchie had this idea called declaration reflects use, where variable declarations mirror the operations you would have to perform on the variable to get a value of the base type. Clever idea, but I don't think it worked out great in practice. Back to the text. What C-like syntax has instead is something you'll often find more valuable in a language: familiarity. I know you are already comfortable with that style because the two languages we'll be using to implement Lox, Java and C, also inherit it. Using a similar syntax for Lox gives you one less thing to learn. A high-level language. While this book ended up bigger than I was hoping, it's still not big enough to fit a huge language like Java in it. In order to fit two complete implementations of Lox in these pages, Lox itself has to be pretty compact. When I think of languages that are small but useful, what comes to mind are high-level scripting languages like JavaScript, Scheme, and Lua. Although three, Lox looks most like JavaScript, mainly because most C syntax languages do. As we'll learn later, Lox's approach to scoping hews closely to Scheme. The C flavor of Lox we'll build in part 3 is heavily indebted to Lua's clean, efficient implementation. Side note, now that JavaScript has taken over the world and is used to build ginormous applications, it's hard to think of it as a little scripting language. But Brendan Eich hacked the first JS interpreter into Netscape Navigator in 10 days to make buttons animate on web pages. JavaScript has grown up since then, but it was once a cute little language. Because Eich shaped JS together with roughly the same raw materials and time as an episode of MacGyver, it has some weird semantic corners where the duct tape and paper clips show through. Things like variable hoisting, dynamically bound this, holes in arrays, and implicit conversions. I had the luxury of taking my time on Lox, so it should be a little cleaner. After all, the two languages we'll be using to implement Lox are both statically typed. Okay. Dynamic typing. Lox is dynamically typed. Variables can store various values of any type, and a single variable can even store values of different types at different times. If you try to perform an operation on values of the wrong type, say dividing a number by a string, then the error is detected and reported at runtime. There are plenty of reasons to like static types, but they don't outweigh the pragmatic reasons to pick dynamic types for Lox. A static type system is a ton of work to learn and implement. Skipping it gives you a simpler language and a shorter book. We'll get our interpreter up and executing bits of code sooner if we defer our type checking to runtime. Automatic memory management. Yeah, this is going to be a GC language. Data types. In Lox's little universe, the atoms that make up all matter are the built-in data types. There are only a few: booleans, numbers, strings, and nil, which is going to be the same as in languages like Lua, I think, or maybe what? In languages like Lisp and Ruby and Elixir and Go. Okay, expressions. If built-in data types and their literals are atoms, then expressions must be the molecules. Excuse me. Arithmetic. Logs features the basic arithmetic operators you know and love from C and other languages. Addition, subtraction, multiplication, division. These sub-expressions on either side of the operator are operands. Because there are two of them, they are called binary operators. It has nothing to do with the ones and zeros use of binary. Because the operator is fixed in the middle of the operands, they are also called infix operators, as opposed to prefix operators, where the operator comes before the operands, and postfix, where it comes after. One arithmetic operator is actually both an infix and a prefix one. The minus operator can also be used to negate a number. There are also some operators that have more than two operands, and the operators are interleaved between them. The only one in wide usage is the conditional or ternary operator of C and its friends. As condition question mark, then arm, colon, else arm, semicolon. Some call these mixed-fix operators. A few languages let you define your own operators and control how they are positioned, their fixity. All of these operators work on numbers, and it's an error to pass any other types to them. The exception is the plus operator. You can also pass it to two strings to concatenate them. Comparison and equality. Moving along, we have a few more operators that always return a Boolean result. We can compare numbers and only numbers using ye-old comparison operators. We can test two values of any kind for equality or inequality. Even different types. Values of different types are never equivalent. I'm generally against implicit conversions. Then we have logical operators. The not operator, a prefix exclamation mark, returns false if its operand is true, and vice versa. The other two logical operators are control flow constructs in the guise of expressions. An AND expression determines if two values are both true. It returns the left operand if it's false, or the right operand otherwise. Side note, I used AND and OR for this instead of ampersand and pipe because logs doesn't use ampersand and pipe for bitwise operators. It felt weird to introduce the double character forms without the single character ones. I also kind of like using words for these since they are really control flow structures and not simple operators. Back to the text. And an OR expression determines if either of two values or both are true. It returns the left operand if it is true and the right operand otherwise. The reason AND or OR are like control flow structures is that they short circuit. Not only does AND return the left operand if it is false, it doesn't even evaluate the right one in that case. Conversely, contrapositively, if the left operand of an OR is true, the right is skipped. 344. Precedence and grouping. All of these operators have the same precedence and associativity that you'd expect coming from C. When we get to parsing, we'll get way more precise about that. In cases where the precedence isn't what you want, you can use parentheses to group stuff. Since they aren't very technically interesting, I've cut the remainders of a typical operator menagerie out of our little language. Also, we can try to execute this example from earlier on. So if var minimal equals 1 and var maximum equals 8, then var average equals min plus max divided by 2. Print average. Nice. Since they aren't technically interesting, I've cut the remainder of the typical operator menagerie out of our little language. No bitwise shift modulo or conditional operators. I'm not grading you, but you will get bonus points in my heart if you augment your own implementation of logs with them. Those are the expression forms, except for a couple related to specific features that we'll get to later. So let's move up a level. Statements. Now we are at statements. Where an expression's main job is to produce a value, a statement's job is to produce an effect. Since by definition statements don't evaluate to a value, to be useful they have to otherwise change the world in some way, usually modifying some state, reading input or producing output. You've seen a couple of kinds of statements already. The first one was print hello world. A print statement evaluates a single expression and displays the result to the user. You've also seen some statements like some expression. Side note, making print into the language instead of just making it a core library function is a hack. But it's a useful hack for us. It means our in-progress interpreter can start producing output before we've implemented all of the machinery required to define functions, look them up by name, and call them. An expression followed by a semicolon promotes the expression to statementhood. This is called, imaginatively enough, an expression statement. If you want to pack a series of statements where a single one is expected, you can wrap them up in a block. Blocks also affect scoping, which leads us to the next section, variables. You declare variables using var statements. If you omit the initializer, the variable's value defaults to null. Okay. Side note, this is one of those cases where not having nil and forcing every variable to be initialized to some value would be more annoying than dealing with nil itself. Okay, let's see. Var variable nil variable equals to variable can be assigned to any value, and then it now equals 2. Great. Once declared, you can naturally access and assign a variable using its name. Var breakfast equals bagels, print breakfast. What's beignets? Beignets? How is it pronounced? Beignet. Beignets. Breakfast equals beignet. Print breakfast beignet. Side note, can you tell that I tend to work on this book in the morning before I've had anything to eat? I won't get into the rules for variable scope here because we're going to spend a surprising amount of time in later chapters mapping every square inch of the rules. In most cases, it works like you would expect coming from C or Java. Control flow. It's hard to write useful programs if you can skip some code or execute some more than once. Yeah, so an if statement, a while loop, all of these work exactly like in C, except that you cannot use A++ because this postscript operator is not implemented. Functions. A function call expression looks the same as it does in C. Make breakfast, bacon, eggs, toast. You can also call a function without passing anything to it. Unlike in, say, Ruby, the parentheses are mandatory in this case. If you leave them off, the name doesn't call the function, it just refers to it. A language isn't very fun if you can't define your own functions. In logs, you do that with fun. Side note, I've seen languages that use fn, fun, func, and function. I'm still hoping to discover a functi or functio somewhere. Now is a good time to clarify some terminology. Some people throw around parameter and argument like they are interchangeable, and to many they are. While we're going to spend a lot of time splitting the fineness of downy hairs around semantics, so let's sharpen our words. From here on out, an argument is an actual value you pass to a function when you call it. So a function call has an argument list. Sometimes you hear actual parameter used for these. Hang on, I'm going to check how much is left of this chapter. Classes, prototypes, classes in logs. Okay. Okay, so basically I'm tired, so I assume the viewers are also tired. So I'm going to skip the rest of this chapter for the purposes of this video. I probably will also read it if this video is successful at all. And I'm hoping to make the actual video when we start writing the interpreter tomorrow. And if you have enjoyed this video, please consider liking and subscribing, and or telling your friends about at least this amazing book. And if you did not enjoy it, please roast me in the comments. This is also very helpful for the YouTube algorithm. Also, I actually wanted to make something more ambitious, but it turns out that the YouTube algorithm wants me to spit out a lot of content. It doesn't have to it doesn't necessarily have to be high quality content. So I'm just going to spit out a lot of content. And also it turns out that the most successful part of my channel have been the Kernighan and Ricci videos. So I'm also hoping that if we have a nice book like this one, and if we just read it and do the exercises on screen, somebody may like it. And my name is Karol Moros, and you have been watching Make Programming Fun Again. Bye.